Okay, let's look at the solutions for the practice exam. Here we have question 1, calculate the freezing point of a solution of 400 grams of ethylene glycol dissolved in 500 grams of water. So freezing point depression, so we need to find the molality of that ethylene glycol solution. Okay, so we've got 400 grams of this, but and we have its molar mass, so we need to find how many moles of the solute we have, and then find out how many kilograms of solvent, and we can find our molality. So we have C2H6O2, carbon's 12, so 2 times that is 24, plus the 6 hydrogens is 30, plus 16 and 16 from the 2 oxygens, that should be about 62 grams per mole. So 400 divided by 62 is going to get us 6.452 moles of that ethylene glycol. And then we can put that over our mass of our solvent, water, in kilograms. We have 500 grams, so that is 0.5 kilograms. So we have a 12.90 molal solution of ethylene glycol. Ethylene glycol is a covalent compound, so there's no Van Hoff factor here. So we wanted to factor that in. So we're just going to take the molality times, we want the freezing point depression constant, so we want the K sub F. We get 24, and it's freezing point depression, so we would take our normal freezing point, 0 degrees Celsius, we would subtract the 24 from that, and we'd have negative 24 degrees C as our new freezing point. Let's see here. No, that's not what I wanted to do. Oh, here. Perfect. All right. Problem 2, endothermic reaction with coal produces. So we've got solid carbon plus gaseous water goes to form carbon monoxide and hydrogen gas. We're told it's endothermic. So that means heat. A little smaller. Heat is going to be a reactant. So which of the following will produce more hydrogen gas? So we want to push the reaction to the right. Adding more carbon to the reaction, that won't do anything because carbon is a solid. It's not in the equilibrium expression. Adding more H2O, that will shift it to the right as we add a reactant. That's going to push it and produce more of our hydrogen gas here. And then other option, raising the temperature, that would be like adding more heat. And that would also do that. So the answer should be 2 and 3, E. All right, write the equilibrium expression for the following reactions. So again, we've got 2C plus O2 goes to form 2CO gas, and technically that should look like that. What's the equilibrium expression? So we want anything that is a gas or is aqueous, anything that isn't solid or pure liquid, and we're going to do products raised to their coefficients over reactants raised to their coefficients. And carbon is a solid, so that gets left out. And this would be answer choice B. Which of the following is not a Lewis base? So Lewis base is an electron pair donor. So we want to find things that have extra electron pairs. Well, the nitrogen's got a lone pair on it, so it would be a good Lewis base. Our oxygen, of course, has two lone pairs on it. It would be a good Lewis base. Our carbon here and our hydrogens have no lone pairs on them. And our Cn minus, this has actually an extra negative charge, has a lone pair on that nitrogen. That would be a good Lewis base. So the only one that would not be a good Lewis base would be our CH4 here, or answer C. Equilibrium constant for a specific reaction is 1.4, okay? Oop, come on. 1.4 times 10 to the negative 5. And that's our K. That's a small. So K is very small. Oh. And then that's the same as 0.0000014. So because of that, that means the number on the top, or the concentration of our product, is very small compared to the bottom. So we can't tell how fast the reaction will go, so we don't know if equilibrium is reached quickly or slowly. Equilibrium has nothing to do with that. The kinetics do, so we throw out A and B. We know in this case, though, that the concentration of the reactants, or the number on the bottom, must be larger than product, the number on the top. So that would be answer C. Six, in a reaction mixture containing only reactants, so whatever we happen to have here, but if we have only reactants and no product, then we're going to get Q, our equilibrium constant, equal to 0, which would mean, yeah, the reactants would be 0. That's also D. Determine the osmotic pressure of a 0.56 molar solution. So we have 0.56 molar solution of NaCl, and the water is 55 degrees, and we're told that the Van't Hoff factor for our sodium chloride is 1.9. So our osmotic pressure should equal M, the molarity, times RP. So our molarity is 0.56. Yep. So we can just go 0.56 times our I, 1.9 times R, 0.08206, times our temperature in Kelvin, be 28.6 atmospheres, which is A. So if it's pH of a solution containing 7.8 times 10 to the negative 6 molarities for the concentration of OH minus or hydroxide. So a couple ways we could do this. We could take the negative log of this. That'll equal our POH. Which is 5.10. We can subtract that from 14 and get 8.90, or I could take the autoionization constant of water divided by the hydroxide ion concentration, get the concentration of the hydronium ion. There we go. If I take the negative log of that, then I get the same thing. So that would be answer C. Determine the pH of a 0.38 molar solution of H2C6H6O6 and ascorbic acid. It's a diprotic acid. So our first ionization constant for the first acidic hydrogen is 8 times 10 to the negative 5. And for the second one, it's 1.6 times 10 to the negative 12. So we're going to start with the higher ionization constant. So we're going to have H2C6H6O6 concentration. That's going to have be plus H2O. We're going to protonate the water, give us our hydronium. Oops. And then the conjugate base of that. This starting concentration is 0.38. This is 0. This is 0. We only have reactant. We don't have product. So we're going to lose X of that, make X of these. So then, actually, let's go back to this. So our Ka1 is 8.0 times 10 to the negative 5. That's going to be equal to X squared over 0.38 minus X. We're going to do the X is small approximation. We're going to get 3.04 times 10 to the negative 5 equals X squared. Take the square root of both sides. And X is equal to 5.51 times 10 to the negative 3. That is the same thing as our hydronium ion concentration. So if I take the negative log of that, we should get the pH, which is 2.26. And then our Ka2 is much, much smaller than Ka1. So similar to if we had a mixture of two weak acids where one had a much larger Ka than the other, we would only need to look at the one with the large Ka, so we don't need to bother with the second protonation here, the Ka2, that second acidic hydrogen. We've just got our pH right there, 2.26, which would be answer B. For units of K in the following, so I've got rate constant, we've got X, first order with respect to X, first order with respect to Y. But if we have two components and they're both first order, then we are second order overall. And that means we'd have molarity times molarity, which would be molarity squared. So if I want to get to molarities per second as my overall rate, then whatever K is, if this is molarity squared, we can see K is going to have to be 1 over molarities per second, because when I take that times this, that's going to cancel one of these, and we'll end with our molarities per second. So that should be answer B. Reactions found to have an activation unit. Okay, so we're going to do the 2-point form Arrhenius equation. So we've got our activation energy here is 108 kilojoules per mole. Rate constant 4.6 times 10 to the negative 6 at 275 K. And then what we want to know is what's our rate constant at 366 K. So for that, we've got the natural log of 4. Actually, we'll make that, we'll make that K1 or K2. Okay, so 4.6 times 10 to the negative 6. We have K1 on the bottom. That's what we're trying to solve for. Our activation energy, 108,000 or 108 kilojoules or 108,000 joules per mole. I'm going to convert it to joules because our R constant is units of joules. And then the units will agree. And then 1 over T1, which was the 366. Oh, hopefully you can still hear me. Looks like the microphone died. I'm going to stop, I guess, there.